Let's assume that the listeners don't care about how we smell. Why should they still be interested, either from an intellectual standpoint or like a functional standpoint, in the way that olfaction works? Do people who study olfaction because they want to understand smell, or are there other things that are interesting about it?
For me, the sense of smell is a window to the consciousness, to the brain, and it's a very transparent window. The system have much less computation and much less processing before getting to the cortex and create objects. We manipulate these objects, olfactory objects, and it's easy to work with the system. But at the same time, we have two more reasons. First of all, it's a fascinating system. We know how color vision works. We invested so much in understanding vision and hearing, and olfaction is a big mystery. And I do care about olfaction deeply. I do care how we smell, what happens in the brain when we smell the rose or when we smell the coffee, how we discriminate odors, what actually the odor spaces can be manipulated, how they're mixing, and it's a lot of unsolved problem. It's a huge intellectual challenge. And the third reason, we're moving to a very new era this time, because we all are surrounded by organic molecules. We all are smelling all the time. We don't have sensors. We don't have receptors. We don't take advantage of that. And over evolution, this is probably a unique system that allows maybe us to have a look at this world of molecules, world of chemistry, that it's not yet here under our, we don't have access. We build a very complicated devices like gas spectrometry, gas chromatography, mass spectrometry, but the nose does it for us. We know much more about genetics, we know much more about cellular processing, but we don't know much about the odors around us. And nature does know. Nature takes care of that. And we actually have now access to actually understand how the nose, the device deals with that. And this is a fascinating subject. I start reading how we can smell disease, how we can smell, other stuff, because animal can do this. And that's fascinate me, to the same level as we create objects in the brain.
So what you're saying essentially, Dima, is that we have microphones that are significantly better than, anything we can say or hear. We have speakers that can reproduce what we say much better. We have cameras that are much better than our eyes. But, there's no chemical detectors that are anywhere near the complexity, even of our human, quite underutilized and undertrained noses, right? And if you go through more trained animals,
this is completely untapped world, and I think that it's a million discoveries will be if we have a right detection tools.
There's a lot of interesting problems to be solved here because this technology has never been released in the world. Nobody's ever had a real-time portable sensor out there pulling down this massive quantity of molecular data. And I think we're going to start to uncover some really interesting things about the world from that, across different industries, from pollutants in the environment and how they affect all sorts of different things. We feel it's a very meaningful endeavor and feel it's going to be a profitable endeavor too. And if you want one controversial statement, Matt.
Which I would love, yes.
My wager is going to be that in the long term, using a BMI, we're going to be able to detect things better than a trained animal. The reason for this doesn't have to do with the filtering in the olfactory bulb. It has to do with the kinetics of gas flow. Detect things that are at great distance by having an a priori understanding of the speed at which those molecules arrive. So the pattern might not exist there in the dog's mind to be able to pick up. It might not have a holistic pattern that it's detecting in one sniff, but that signature might be stretched out in time and we might be able to pick that up.
That's interesting. Andreas, I think you've done a little bit about odor localization in your lab.
We're looking at odor plumes. So not only the chemical structure of odors, but actually the temporal structures, how concentrations change rapidly over time. And we find that mice can actually detect these very rapid fluctuations at time scales of tens of milliseconds or faster. And there's a lot of information in that, which we know from the difficult study of turbulent airflow. But if we then do some kind of population recordings in the olfactory bulb, be it with electrophysiological means or imaging or so, we can quite easily pick up signatures about the temporal structures of odors with very, very high precision, much more easily than training animals and performing the same kind of discrimination. So my sense from all those combination of complex behavioral experiments and different physiological experiments and a variety of linear and nonlinear classifiers thrown at data, certainly that as soon as you start having, let's say, a tens or at least 100 recording sites, you almost inevitably are much better in decoding the specific type of olfactory stimulus than animals show in trained behavior if we train them over periods of days or weeks. So I'd be very much with you guys in saying that you can extract much more from the actual activity pattern that you will be able to record than you can train animals to report behaviorally.
Yeah. Gabe, that must feel good because your bet turned out to be right within about 5 minutes of making it.
Yeah.
I'm glad you consider my statement to be a final judge on Gabe's bet, but
I was really kind of referring to things that, and I think that definitely adds to it, but things that are very far off in the distance. Like if you have a dog that's trying to detect the scat of a whale 2 kilometers offshore, and the identifying pattern, which represents that scat, is coming in very slowly, right? Like 2 minutes later, or 50 seconds later, right? Not something that's in a small temporal fluctuation, but something that's spread out in time.
So gas chromatography, where the medium for chromatography is the air, and the distance is very long.
Yeah.
And you can computationally integrate over much longer time scales that animals would typically integrate.
Exactly.
You would expect that for normal behavior, you need to integrate over maybe a few seconds, but not tens of seconds a minute.
I would say that the challenge here, to my opinion, I think that you can train an animal specifically to detect one specific feature of the signal. And if the task will be to integrate or just opposite, to take a very brief plume, you can train an animal. The advantage of having brain-machine interface that we don't need to train. We can collect all information and then post-factum extract whatever we want, whenever we want, and as much as physical limits allows.
So and those models are transferable between animals too, as long as you have, as you were saying, the fiduciary markers.
Yes, the physical limit, probably an each specific detection task can be achieved by the animal as good as with BMI. But flexibility between the tasks and flexibility between the targets is what is very hard to achieve with the behavior and get multidimensional report.
One very, very interesting aspect of the digitized sense world is that once you have it digitized, you have the ability to go back in time and parse that data for signatures which you didn't currently have at the time of recording the data. So if you're looking for when did a new virus cross through this airport and you're looking for the fingerprint of that virus, you can go back, parse the data, and see if there's any recording of that virus and when it happened and where it happened. That's a really, really useful feature of digitizing the sense space.